Welcome back. We were in the midst of figuring out the Laplace transform of sine of at when I was running out of time, and so I just, this is the definition of the Laplace transform of sine of at. I said that also equals y. This is going to be useful for us since we're going to be doing integration by parts twice. So I did integration by parts once, then I did integration by parts twice. I said, don't worry about the boundaries of the integral right now. Let's just worry about the indefinite integral, and then after we solve for y, let's just say y is the indefinite version of this. Then we can evaluate the boundaries. We got to this point, and we made the realization after doing two integration by parts and being very careful not to hopefully make any careless mistakes. We realized, wow, this is our original y, right? If I put the boundaries here, that's the same thing as the Laplace transform of sine of at, right? That's our original y. So now, and I'll switch colors just to avoid monotony. This is equal to, actually, this is y. This is equal to y. Right? That was our original definition. So let's add a squared over sine squared y to both sides of this. So this is equal to y plus, I'm just adding this whole term to both sides of this equation, plus a squared over s squared y is equal to, so this term is now gone, so it's equal to this stuff. And let's see if we can simplify this. So let's see if we can, let's factor out an e to the minus st. Actually, let's factor out a negative e to the minus st. So it's minus e to the minus st times sine of, well, actually, let's factor out it. Well, let me just write 1 over s sine of at minus 1 over s squared cosine of at. I really hope I haven't made any careless mistakes. And so this, we can add the coefficients, so we get 1 plus a squared over s squared times y. But that's the same thing as s squared over s squared plus a squared over s squared. So it's s squared plus a squared over s squared y is equal to e minus e to the minus st times this whole thing, sine of at, minus 1 over s squared cosine of at. And now, this right here, this is, since we're dealing everything with respect to dt, this is just a constant, right? So we could say a constant times the antiderivative is equal to this. This is as good a time as any to evaluate the boundaries, right? If this had a t here, I would have to somehow get them back on the other side, so that, because the t's are involved in evaluating the boundaries, since we're doing our definite integral or improper integral. So let's evaluate the boundaries now. And we could have kept them along with us the whole time, right? And just factored out this term right here. But anyway, so let's evaluate this from 0 to infinity, and this should simplify things. So the left-hand side of this, the right-hand side of this equation, when I evaluate it at infinity, what is e to the minus infinity? Well, that is 0. We've established that multiple times, and now it approaches 0 from the negative side, but it's still going to be 0, or it approaches 0. And then that times, well, what's sine of infinity? Well, sine just keeps oscillating, right, between -1 and +1, and so does cosine, right? So this is bounded. So this thing is going to overpower these, and if you're curious, you can graph it. This kind of forms an envelope around these oscillations. So the limit as this approaches infinity is going to be equal to 0. 0. And that makes sense, right? These are bounded between 0 and -1, and this approaches 0 very quickly. So it's 0 times something bounded between 1 and -1. Another way to view it is the largest value this could equal is 1 times whatever coefficient's on it, and then this is going to 0, so it's like 0 times 1. Anyway, I don't want to focus too much on that. You can play around with that if you like. Minus this whole thing evaluated at 0. So what's e to the minus 0? Well, that is e to the minus 0 is 1, right? That's e to the 0. We have a minus 1, so it becomes plus 1 times, now sine of 0 is 0, minus 1 over s squared cosine of 0. So what is 1 over cosine, let's see, cosine of 0 is 1. So we have minus 1 over s squared minus 1 over s squared times 1. So that is equal to minus 1 over s squared. And I think I made a mistake because I shouldn't be having a negative number here. So let's backtrack and let's see where that mistake might. Maybe this isn't a negative number. Let's see, infinity, right? This whole thing is 0 minus. Let's see, when you put 0 here, this becomes a minus 1. Yeah, I'm getting a. Let me see where my. So either this is a plus or this is a plus. Let's see where I made my mistake. E to the minus st. Oh, I see where my mistake is, right? Up here, where I factored out a minus e to the minus st, right? Fair enough. So that makes this 1 over s sine of at. But if I factor out a minus e to the minus st, this becomes a plus, right? It was a minus here, but I'm factoring out a minus e to the minus st. So that's a plus. This is a plus. Boy, I'm glad that was not too difficult to find. So then this becomes a plus, and then this becomes plus. Thank God. It would have been sad if I wasted 2 videos and ended up with a careless negative number. Anyway, so now we have s squared plus a squared over s squared times y is equal to this. Multiply both sides times s squared over s squared plus a squared, and divide both sides by this, and we get y is equal to 1 over s squared, 1 over s squared. And actually, let me make sure that that is right. It's 1 over s squared, right? Y is equal to 1 over s squared times s squared over s squared plus a squared. And then these cancel out. And let me make sure that I haven't made another careless mistake. Because I have a feeling I have. I have a feeling I have. Yep, there, I see the careless mistake. And it was all in this term. It was all in this term. And I hope you don't mind my careless mistakes, but I want you to see that, you know, I'm doing these things in real time, and I'm human, in case you haven't realized already. Anyway, so I made the same careless mistake. So I factored e to the minus st here. So it's plus, but it was a over s squared. So this is an a. That's an a. And so this is an a. And so this is an a. And so this is an a, right? This was an a. And so we're left with, and this is the correct answer, a over s squared plus a squared. So I hope those careless mistakes didn't throw you off too much. You know, these things happen when you do integration by parts twice with a bunch of variables. But anyway, now we are ready to add a significant entry into our table of Laplace transforms, and that is that the Laplace transform. I added an extra curl there. That was unnecessary. Let me do it again. The Laplace transform of sine of at is equal to a over s squared plus a squared. And that's a significant entry. And maybe a good exercise for you, just to see how fun it is to do these integration by parts problems twice, is to figure out the Laplace transform of cosine of at. And I'll give you a hint, it's s over s squared over s squared plus a squared. And it's nice that there's that symmetry there. Anyway, I'm almost at my time limit, and I'm very tired working on this video, so I'll leave it there, and I'll see you in the next one.